Okay, we might start. Welcome to my talk, everybody. I'm going to look at using some modern tooling in CppCon and the constexpr tools to build some compile time utilities and some resource generation, and we're going to do some string compression as well. So we can use the constexpr features in CppCon to generate data from code at compile time. We can use that sort of ability to then construct things like lookup tables, configuration fuses, compressed strings, and USB descriptors as some examples. Now, this talk is going to introduce some of the ways I've found to do it, and we're going to look at a fair amount of code. But I'm not going to go into huge depth in the way the string compression works or the way the USB descriptors work. I'm just going to highlight the interesting facts. All the code for this, and along the way, I'll introduce you to some libraries that I created, which are now available on GitHub, as is this presentation as well. And I'll provide links for that shortly. We'll discuss some techniques I found when I was building these libraries. And realistically, I'm not an expert in C++. I found most of this stuff through experimentation. So I thought it would be interesting for others, especially in the embedded space, where we can use these tools to help us create more robust code and better tooling. So we'll start with a very, very brief introduction to constexpr, and I'm sure some other talks today have already covered a lot of this stuff. Especially, I'd recommend going and listening back to Jason's talk earlier this morning. So constexpr, basically, it specifies that a function or a variable can appear in a constant expression. So in C++, the constant expression can then be assigned to, it can then be used for things like in types as well. So basically the constant expression is then evaluated at compile time. And we can use that for things like an array size, non-template type parameter, and things like that, and which we're going to exploit to build types and fill them with data at compile time. So constexpr variables, they have to be a literal type. That basically means a scalar, like an int or a character or something like that. They have to be an array of literals, or a structure or a union or a class or something like that. There's a few constraints there, but I don't really want to go in depth with that. We can return closure, a constexpr variable can contain a closure type, i.e. a lambda. The variable must be immediately initialized, which means that when you declare it, you must give it a value so that the compiler knows what to store there. And it implies const. So if we have a very quick example, we declare a constexpr int and give it a value. We could create a constexpr array and fill it. And we can then use those things. So note that it's constant, so I can't add one to base, but I can use it in an expression. Constexpr functions is where the real fun is. They must return a literal type or void. So if you have a constexpr method in an object that does some work, it can do that. It doesn't have to return a value. It must ensure that all members of any return value are fully initialized. And the compiler also works very hard to check for undefined behavior and not let you make any. So it's quite useful in that sense as well. You can have a constexpr constructor, which we will use to create some classes and types that we can use at compile time. And again, if you're a constexpr constructor, you must initialize all members fully in your object. Parameters can be to functions, constexpr functions can be any literal type. And an example like this. So we have a function called makeBigger that takes an integer and returns it 100 times larger. It's quite a simple thing, but we're going to build on that and get some complex behavior out of it. So as of C++20, constexpr functions can now contain practically all the code. You can even allocate memory in them, as long as that memory is freed before you return. Const eval specifies that a function must produce a compile time constant. That means it's then an error if you don't provide it constant values to evaluate. That implies constexpr. Now there's another one called const_init, which you can apply to a variable, and that says that the variable has static initialization, which means it has to be initialized at compile time. So it can be initialized from a constant expression. It can also be zero initialized, but that's not particularly useful. The value is computed at compile time and stored into the binary. You can have constant int variables which are mutable or constant. So if we have a look at a simple example here, we've created a mutable foo, which we've assigned the value 10, and we can modify that. And we've also created a constant int called bar, which we can't modify. So when we want to, when I started doing this, I was looking for ways to improve the way I build things like configuration registers and USB descriptors for a project I was working on. And eventually in talking to some people, I found a few other opportunities to use it. And so I'm planning on presenting 4 different things today. I'm going to look at lookup tables. We're going to look at configuration fuses, so microcontroller, hardware configuration fuses. We're going to look at a compressed string table, and we're going to look at building USB descriptors. So this is all available or linked from the repository here, and that should be publicly available now. If it's not, let me know after the talk, and I'll make sure it's up and running. So why do we want to do this? Well, it means that we can build things without external tools. So we can generate complex data that we need for our system at runtime without having to generate it externally. We can use the type semantics in C++ to enforce correctness, and because pushing limits is lots of fun. So let's start with lookup tables. So we're going to make a lookup table that does linear interpolation for us. Now, a little bit of a warning, I'm using the GCC extension to allow for the standard math standard math functions to be constexpr. They currently are not. That's a GCC only extension. There are some concerns around that to do with how you handle errors and rounding and compile time versus runtime, different values and things like that. So if you're interested in that issue, P1383 is a good is a thing to go and have a read of. So I should say I'm probably not very good at taking questions during the thing. So I just noticed someone put up a hand. If you could go to the Q&A tab and type a question in there, I'll see that, and I'll be able to respond to that. Okay. So we're going to try and build a simple lookup table that's going to calculate sine for us based on degrees, not radians, just because. So we can set up code that looks something like this. We can have a function that converts degrees to radian. Again, it's constexpr. We create a function, call it sine degree, that takes degrees and returns the sine of it. And then we use a type that I'll show you in a second called lerp table. We tell it it's using a float, and we want 32 entries in our table. So the number of entries really defines the precision in this case. And we see we're making a table between 0 and 90 degrees using our provided function. So that the non-template parameter, the 32, then it really does affect how closely the points align with the real function. So the more points you have, the closer your estimation will be, because we linearly interpolate between those two sets between two values. And again, we can see that at compile time, we can static assert that we get correct values. So sine of 30 degrees is half, so within some margin of error. The alert table looks approximately like this. So it takes it's a templated struct, and it takes the type to use to store the values, and it takes a number of entries you wish in a non-type template parameter. And we're going to have an operator that effectively evaluates the value given a specific input, and we'll have a helper function that builds the table for us, and it does that by stepping through all the entries and recording the values. And you see we'll just store that in a std array of entries, and those entries are simply points in the function space, so input to output mapping. If we have a look at our implementation of make table, we're taking a function in, and we'll see other ways to bring in functions later on. For example, you can use auto, the auto parameter stuff you can do now in C++20. Now, this static method simply allocates a table. It sets the first and last entries to the values explicitly to avoid sort of rounding during stepping, and then fills in the remainder of the values in a for loop in the middle and returns a table. It's pretty straightforward, like you would do to do this at runtime. Then when we want to look up a value, we take the input provided, we clamp it within the range of the minimum and maximum inputs. And this is to ensure that obviously we don't overflow our bounds when we're searching for where the value lies. Again, you might want to consider alternate error handling strategies like throwing in an exception or something like that if you're allowed to use exceptions, or providing some other indicator. We then apply, again, another standard algorithm, std lower bound, which will find the first element that is not less than the value we've provided, we've asked for, and we search the input in our array, get access to our entry, and then if we happen to be the initial value, we're not going to have a previous element to interpolate from, so we just check that, and that handles landing on an exact match. And also it handles the first entry so that we don't access out of bounds things. We work out the previous entry, and then we work out the distance between the two for our required value, and use the alert function to do the interpolation and return our value. Sorry, there's a question here. Is there a reason you're using constexpr rather than constval, which will guarantee this gets executed at compile time? The only reason I'm not is I will look at that sort of stuff in later slides. So yes, you could make that constval, and I think what we're talking about is, this the constexpr auto degree sine table thing. Yes, we could make that constexpr. Constval and ensure it, but I'll show that there's other things we can do with that as well. But it really will almost certainly be evaluated at compile time anyway. And the static assert wouldn't work if it wasn't compile time either. So that's one way you can also check it. So if there are any other questions on that section before we move on, doesn't seem to be anything in the chat at the moment, but I'm conscious that there's probably a small delay between what I'm saying and what you're hearing. No? Okay. We might move on, and if anyone has any questions, I'll try to address them as we go. So if you're working in the embedded space, you almost certainly know what config fuses are. If you're not, a quick introduction. They initialize hardware before the processor starts. So in the microcontroller, it's got lots of different options and settings. Then you need to be able to configure that before the CPU in the microcontroller can even start. The way this is normally done is there are fixed locations in flash memory defined by the manufacturer that says, if you put this bit pattern here, it will configure certain hardware options. And basically, it's a whole series of magic values that you have to read, 200 pages of data sheet to understand. They can set up things like clocks, so how fast your thing's running, what the clock source is. It can set in some larger microcontrollers, you set up memory segments, you can set up protection, watchdog timers, JTAG debugging availability, security options on the code, so whether you can read the code out or anything like that, and quite a bit more. So we will, so currently this is handled in compilers by vendor-specific extensions. So some of these are more directed to the way C is used quite a lot, but it's done the same way for if you're using C++ in those environments. So there can be things like pragmas or similar hash, magic value, magic variable equals magic number sort of scenarios, special macros, and it relies quite heavily normally on C-style hash defines for bit values and things like that. So as you can see, there's not a lot of opportunity for validation or and configuration is potentially quite complex. And indeed, some of the processor vendor tools have GUIs that work out the configuration for you and then provide that generated code. So you can just include it into your project. But I think we can do better. If we strongly type all the configuration registers or build some type-based tooling around what values are correct and things like that, we can leverage C++ to, at compile time, determine whether those settings make sense. We can provide a builder object to help us put together that configuration, or in fact, provide a series of useful defaults. And then at compile time, we render it to a constant knitted object, and we place it in Flash using segments and the linker script. And this was lots of fun. So if we build a very simple example here, let's just say we have two registers, one controls an oscillator mode and one controls a watchdog mode. So we can create a very simple builder. Again, we're not really doing any checking in this case, but we can build tooling to do that should we get an actual device running with this, because we're going to have to do this very specifically for every different device. So we obviously provide some tooling to some functions there to set the watchdog mode and to set the oscillator mode. And again, I've chosen to do that with enum classes. It could be other subtypes that you can configure and pass in, all sorts of ways to do this. We have a build function, which we'll look at shortly. And we have a series of values with sensible defaults. For instance, it might be that the default oscillator mode should be the internal RC oscillator, which is generally a low-speed, low-power oscillator. And we want the watchdog timer disabled by default, for instance. So if we have a look at our build process, what we're going to do is we're going to pretend we have two 32-bit registers. We're going to also pretend that we need to do some computation on the values we need to put into those registers. For instance, we need the actual value and its complement in that register in different bit locations to show validity. And the process we go through is allocate an array of the correct size. This could also be strongly typed. You could create a structure and map it into the right map all the values into the right places. But then you have to worry about packing and alignment and things like that and making sure that that's correct. The approach I've taken here is literally just to render the data. So we can then do any computation we want and put it into the registers and output that. So how would we use that? We would do this. So we have a constant init value that we initialize from a lambda, which we immediately invoke. So the lambda function is, the capitalized lambda is constexpr at that point. And the constant init ensures that it's immutable and it's built at compile time. So the constant init and const, it's a little bit of a handful, mouthful there to get constant init and const on the type, but that's what we have to do. That makes it immutable. The GNU section attribute tells us that we want to drop it into a name section, which we're just calling config registers for now, and we'll get to how we use that in a second. And the other thing we need to do is tell the compiler that we're actually using this value and not to discard it, because we're not going to reference this value in code anywhere. It just has to be there in the final output. So to make all this work, we have to tie it together with the linker script. So linker scripts defines a layout for the final binary image. It maps sections from our program. So when we compile code, it goes normally into a text segment, and that fills memory regions that deal with the program. We're going to create our own segments for certain things, and we're going to put we're going to place them in memory. So we map sections into memory regions. Normally, you never need to know about this sort of stuff until you do. So we need to ensure our config registered variable is placed in a very specific location for the hardware, because otherwise it just won't work. So let's pretend we need to put that at address 100 hex. And we'll define memories in the script and add one for config registers, and we'll add, and then we'll map using a linker script the config registers segment from our program into that area. So here is an example of the world's worst linker script. Please don't use this, but it shows you the technique. If you're going to play with this, I suggest you find the linker script that's used on your, by default in your hardware, and work from that. It's likely to be significantly more complicated than this, and you might need to clean it up a fair amount. So as we can see, we define some memory regions, config starting at 100 hex, and it's a length of 8, which is two 32-bit numbers. And then I'm just going to create another program space at 1000 hex that is, we'll pretend that's where our code goes. So we start defining sections. So note we define a section called config registers, which maps to the section we placed our config values into. And we tell the linker that we want to keep all the config registers from any object file coming in and place it into that config, the config memory region. And we do that using this redirector here. That tells us that we want to write into this location. So the linker will go through every object file looking for these sections and join them all together and put them in this region. Now, the interesting thing is, if you define it in multiple places, you're going to run out of space because we've set it up very carefully, and then you'll get a linking error. In this example here, just to make this work so I could show you it, I then dumped text and data and BSS, which are other segments which are quite common, into the standard prog space. So if we then use some script to build it and link it against that, we pass in our linker script here, and we create an output. And then I'm going to obj the output, and we'll see what happened. So once we run that, we see we have a couple of sections. We have at 100 hex, we have these two 32-bit numbers, which are our configuration data in the right place and with the right values computed for us at runtime. And then we have a second section, which is our text, which contains our simple return 0 main function here. So are there any questions on that sort of stuff before we move on? So I've got a question from Ryan. Remember hearing that using linker script to place values can pessimize optimizations because it's essentially external. Well, yes, but we're not even accessing this value. We're generating constants that the hardware utilizes before the computer is even running. So the reason we have to do this is because of the way microprocessors work. So their boot sequence literally copies values from specific locations in flash memory into hardware switches to turn things on and off and set them up. So the fact that you may do that pessimization, I'm not really sure on that. I've always worked with linker scripts when I need to make sure that either particular code or particular values are in specific locations. It's sort of a more advanced technique though. Hope that answers your question. Let's move on. Where to next? So we've created some simple resources of known size and type, and that's the interesting point here. We knew when we started that our configuration registers were a particular size, or we've created a function that takes a float and returns a float. So what about varying the output size or type based on the input data? For instance, a USB configuration descriptor can have many interfaces, and each interface can have many endpoints. And all of that then gets concatenated together into a single block of data with calculated sizes and all sorts of things in it. Compressed string data will rely on the content of the string, not necessarily its length, and also the number of strings you wish to compress. So how do we easily, and another question is, how do we easily build libraries to do this sort of complex code, yet present a relatively straightforward interface to a user of the library? So return size and type. The size of an array or a template parameter of a type must be a compile time constant. We can't calculate a size and then define a type from that. And we'll see examples of how we do this in a minute. But unless it's a constexpr constant, we must be able to calculate these values using constexpr functions and constexpr functions within other constexpr functions that are building the content. It means the compiler has to use type information. We can't. That's the only constant data we have at compile time, apart from certain constant values as well, which we can use. We can't pass data into parameters and use that data. We can't pass data into the constexpr function using parameters and use that parameter data to work out type because it's not constant at that point. So how do we pass that data in? Well, we've seen an example of it. We use lambdas. A lambdas call operator can be constexpr, and each lambda has a unique type, and its return type is known at compile time by the compiler. It may not be simple to work out, but it is known. Therefore, we can write helper methods that take a user-supplied lambda, and we can use that to generate the data we need, and that becomes can be done in a constexpr way. And then we can use that desired data to calculate other things. Now, when we do this, where I'm going to be using the auto parameter syntax, but effectively these things are templated functions, but it's a little bit easier to read, I find. So an example of how a library might look. So let's make a library function that returns an array, that takes some values and returns every second one. So the strategy is, if we look down at the bottom, we have a constexpr auto variable, which we assign by the use of the function every second item, and we pass into that a lambda, which returns an array of integers. So it's important that it's a value type, and std_array works really well for this. You could return a structure, but again, a std_array allows you to define different length of data, which we'll find useful in a minute. If we look at the implementation, the lambda is passed in, but essentially that forms part of the signature for the function. You can imagine that as a template type name, T, and then T lambda as the way that really maps. So the first thing we do is we get access to the data that we require. So by calling that lambda function, and we obviously make that a constexpr expression because it can be, and that data is now known at compile time inside this constexpr context. We can then do operations on that. So for instance, work out the length that we want. So we get the size out of that array, divided by 2, and that then it becomes another constexpr expression length. We can then use that length to allocate an array because, again, that length is known at compile time, and therefore the compiler can understand the type that it's building to return out of this function. We'll then, as a quick example, we'll just iterate through that output array and put in every second data element. And off you go. We have, if we look at the size of the test result, it's 3, not 6. So are there any questions so far before we move on to some examples of using these techniques? Okay. So string compression. Now this I have to blame on Jason Turner. He nerd sniped me very well on this one. I was talking to him about some other constexpr code that I'd created, and he mentioned that it would be awesome to be able to do this. So I thought, oh, how hard could that possibly be? So I went for it. Little did I know I'd end up here presenting at CppCon. So amazing for me to do that, I think. I never expected that. So this is a library I've created. It's available publicly. It's got a whole bunch of examples and test code in there to show you how you can use it. What we want to do is we want to map from an enum to a compressed string. And so an enum is essentially like a resource identifier. So we can use strong types when we refer to these strings later on. We're going to use Huffman coding for compression. It should be possible to do a full zip style compression, but I didn't have the time yet to implement that. But this is the underlying compression below part of the compression routine for zip files. When we create the table, we're outputting a structure that has a mapping of the input key to a bitstream location and a length of the original string. We're outputting the compressed bitstream itself, which we build by combining all the strings together. We output a Huffman tree encoded into an array so that we can use that bitstream to decode the underlying characters. And we create a lookup method which returns an iterator over that compressed data. And the reason we want to use an iterator is so we don't have to decompress the entire string and return it. So which would be kind of defeating the purpose of storing the string compressed in the first place. So just a point here, this library is, the code behind this is fairly complex. There's quite a lot of it. I'm only going to touch on some interesting pieces of it. I'm not going to go in depth. Welcome you to go and have a look at the code, and please feel free to reach out to me if you have any more questions. So here's how we want to use it. We have some enum that represents our strings. We have a lambda function. In this case, I've declared it separately, but I could immediately call that inside our string map builder. Sorry, I could pass that as a non-named. You'll see examples of it in the future, but rather than passing in a named lambda, we can just do it straight away in the function call. We call our string map builder, and this is a helper method that then manages the actual process of building it and generating the types. And then in our main function to access it, we can just go, hey map, can I have string number 1, please? And it will return us an iterator. And that iterator will then iterate through the contents of the string, which we can then print out and write to the screen, for instance, or wherever we choose to use it. Now note that I've built this in a way that we can have the keys out of order. We can also skip keys, and if you try to access a key that doesn't exist, you'll just get back essentially an empty iterator. I chose that rather than throwing exceptions or anything like that. Again, that's just a decision that can be done any way we want to. So underneath the string map is actually a string table, which is a simple indexed access into a compressed string. So it's all of that, except rather than having a value type on top of it, it's just a simple integer. And we wrap that. So this is an example of combining multiple layers of library tooling. So we wrap the simple table, the simple string, with some more metadata that allows us to map our input key into an index. Both the string map and string table are usable in the library as first-class objects. So strings and keys are passed into the library using a lambda, providing either a list of string views or a list of mappings of keys to string views. And the reason we're using string view is because it supports constexpr, and the strings that you're encoding are compile time constants. So that works quite handily. The iterator interface, as I said before, is needed to avoid decompressing the entire string and returning a std string, for instance. You could do that if you wish to, but kind of defeats the purpose of having it compressed in the first place if you don't have a lot of memory. Now, a note, this is Huffman encoding, it's not zip. It doesn't get quite as good compression because we're not reusing repeated text elements, but it's a good starting point. It's useful for long strings, but be aware there is a minimum sort of size of the metadata, which we'll see shortly. That means that short strings really don't make much sense. So if we use our example before, we end up with and we map it into a specific section and dump it. This is the data we end up with. At the beginning here, we have our mapping between key value and index for our two strings. Then we have a mapping, and that represents the additional data that the map version has on top of the table version. The table version then provides a mapping between bit address, start address, so the first bit in the string, and the length of the output string. And this is the second string. It starts at bit 2001. Oh, sorry, no, it doesn't. 124. Sorry, and it's that length. And then we see our compressed bit data. So that's basically all of the bit patterns needed for all the strings, all compressed, all concatenated together. And then we have our encoding of the Huffman table. And as we can see, there's quite a few entries in that table, but we need that table to be able to take the bit stream and walk up the tree to work out what walk down the tree to work out the specific character for each step. So as you can see, that has compressed the strings a bit, but if we had larger strings, it would look a little bit more impressive, but it's harder to put it on the slide. So just a brief overview of Huffman coding, if you're not familiar with it. It's an optimal encoding given a list of symbols and their frequency. Again, we can do other things on top of this that mean that we don't have to encode every character. We can encode, using lookbacks, we can encode repeated sections of the text before we then Huffman encode it, which is essentially what zip does. The symbols in our case are all the characters in all the strings. So I chose to take to build a single Huffman table for every string in the map. Now this might be useful if you have a limited number of characters, for instance, like drawing borders or rendering some sort of text-based graphic drawings, things like that. Symbols are all, sorry, I said that. We use a min heap priority queue to build the tree from the bottom up. And what happens there is that we take the least used symbol and combine it with the next least used symbol, join that together into a node, and then we use the frequency of both of those things combined together is the frequency of that node. We then put that back into the priority queue, and then we pull out the next two things. Again, they'll be the next lowest priority, less frequently used. And essentially what happens is we build that from the bottom up, and we generate a tree structure where you can assign bits to going left or right in the tree, and the string of bits required to get to the character becomes the pattern that we encode. So an example of that from Wikipedia, if we encode the text, this is an example of a Huffman tree, we'll generate this. So each character has an associated occurrence count or probability, same in this sort of scenario. And we could choose to say left is 0 and right is a 1. And so to get to an M, we would have a string of 0, 1, 1, 1. And that would represent an M. Okay, so the library process, when it works, it first of all calculates the character frequency table. So essentially it goes through all of the strings and builds a lookup table with 255 entries, i.e. the number of characters there are, and counts how many occurrences are of each. We then use that to build a Huffman tree in memory, which is hierarchical, and it's not really a balanced tree often. It can be quite lopsided, but we can pre-compute how many nodes and things we need to allocate for that. We build a cache that maps then from the string character into its bit stream that's needed for it, and their variable length. They could be 1 bit, 2 bits, 3 bits, 5 bits. After that, we build the encoded bit stream from all of the input strings, and we then build our index data. So we say, what starting position or what starting bit is each string and how long was the original string. And we package all that up we packaged up the Huffman tree down into an array. I use a breadth first sort of walk of that tree to allocate them into an array, and there's indexes in those entries to refer up and down the tree. And we combine all that data together with the Huffman tree, the bit stream, and the index data into our table representation. And then if we were doing the map, we then package that again inside the map to provide the augmented data to map a user supplied type, i.e. an enum, into an index. Sorry, there's a question here. Is there a way you can build a string table where the strings are added to the table where they're used instead of a preset map? No, I don't believe there is, because you have to know the full set of strings at compile time in the one location. I don't believe you can provide a builder in this sort of case. You can't really collect strings together and then go .render. I do remember trying to experiment with something like that and wasn't able to make it work. So unfortunately, as we'll see, there's a few other constraints to building this sort of code in libraries that mean that the code does look a bit different to normal code that we would write, though it does take a little getting used to. There's quite a lot of constraints. So previously we were saying, so pulling out, let's go and look at some of the interesting pieces of the way I've solved some of the problems in this library. I'm not going to go, like I said, into great depths of the exact process of calculating the Huffman tree and everything like that. The code's available. You're more than welcome to play with it. So I said earlier that if we use that auto parameter thing, we can pass in lambdas. The only problem with that is it doesn't really give the caller any clear picture of what we're expecting. So we're going to leverage concepts here to make it a bit clearer to the end user of the function what we're expecting their lambda to generate. So if we look at the bottom one, callable gives iterable keyed string views. This is the concept that says I want a list, or I want an iterator that provides me a key value and a string view. And we're using that structure at the top there, keyed on the user supplied type, and provides a key and a value. The one above that is what we use to build the table variant. So we say I want an iterable that gives me string views. And again, very simple concept specification. There's probably an easier way to do this, but I'm not an expert in this. So if anyone's got any better clues, be welcome some guidance on that. But what this then allows us to do is name or provide more detail to the end user as to what we're expecting to come into the Lambda, and then provide better error messages as well if they don't do that. So if we are now transforming one input type into another type, so our table implementation requires this type, but we're passing into our map with this type, how do we transform from one to the other? And it turns out that we can build a constexpr function that does that mapping. So it takes the keyed string views and returns the callable string views. And the way that works is it returns a lambda. And that lambda essentially does what we do in quite a lot of the other code here. We evaluate the user's function. We work out how many strings we need. Again, we just using standard library tooling here. And we create a suitable array that now contains string views and the number of strings that we need. And we simply copy the values into that and return it. So that then allows us to take the user supplied function and map it into a different function. So modularizing code was the greatest challenge that I found. Needing to calculate compile time constants from user data is the limiting factor. You can't pass it from one function to another as parameters. They're not const. It seems like the compiler could know that it is because it's already in a constexpr thing and it's calling another constexpr, but it can't. It doesn't work that way, unfortunately. So the user supplied lambda often needs to be reevaluated in each context. So if you're breaking your code up into compute character frequency and then compute Huffman tree, that sort of thing, you will end up evaluating the user supplied lambda multiple times, and perhaps the compilers are smart enough to memorize that and provide and not do that work multiple times, but I'm not sure. We can define local lambdas inside a function to sort of contain code and give the sort of give names to pieces of code so that we can sort of modularize in that way. But that does lead to very long methods. And unfortunately, I don't think there is a better way to make that work. So as an example, if we were to build, so this is sort of pieces of my implementation here. So making coding bitstream making coded bitstream takes our strings and generates the bitstream. But to do that, it needs the Huffman tree. So what we're doing here is we'll note that we have to get the lambda and evaluate it in both contexts in order to build this abstraction where we generate the tree separately from doing it inline in this function, which would end up in quite large functions. It looks like we're passing the lambda in here, but remember, this is really just a template instantiation of this function. So we're telling it the type, and we happen to have an instance of it. So at this point, this actually defines a known type, and we can get the tree out as constexpr, and then we can use that tree data in other ways to help name types, similar to what we would do here with the number of strings. So if we would look at a little bit more in depth, here's another example of using local lambdas. So this would be inside of the makes bitstream function. So part of that is we calculate a character lookup table, and that would again call that's another, I haven't shown it yet, but that's a previous lambda, and it evaluates the strings and builds a map of character, well, basically builds an array, not a map, but builds an array of 255 entries, one for each character and account, and does the lookup table isn't that. The lookup table is my pre-computed cache of the characters that are used to the bit encoding for that character, and we'll get into why I had to do that in a minute. The calculate string length basically is a little helper that you pass it a string view, and it will count the number of bits needed to represent every character in that string. If we want to calculate all of the bit lengths that we need, we want to calculate the total bit length we need to store for all of the strings together, then we use the second lambda, which is calculate encoded string bit lengths, and it creates a map of, an array output of the number of strings, and the value in each entry in that array is the calculator length from the previous one. So the output of that is then an array of strings, an array of string lengths. And we can then use that to calculate the total encoded length, and we can just pseudo-accumulate over the top of that array. And again, that becomes a constexpr value, which we can then use that total encoded length later on to look at to define a suitable size to store that data in our outbound type. You notice we're able to use most algorithms. I haven't found one yet that doesn't work, but I can't say I've used all of them. I've used sort, I've used heap functions, push and pop. I've used countif, I've used difference, I've used accumulate, next and previous, things like that. But it's not so great for containers. We can use std array, and std vector is waiting for compiler support to be constexpr, but we don't have a lot else as far as I'm aware. So I had to build my own constexpr tooling and try to make them as simple as I could. So I built a priority queue, I built a list, and I built a bitstream, which is kind of analogous to a std bit set. I would really like more constexpr containers that would make this sort of experimentation a lot nicer. We can do heap allocations. I'm conscious that we're running out of time, so we might speed through this pretty quickly. We can allocate heap, but we have to free it before we leave in the context. It means you can't return it from one constexpr context into another constexpr context. So a function, even if it's being called within a constexpr context, can't return allocated memory. You have to return a literal type. I used a list internally for when I was doing the breadth first traversals, but I didn't allocate nodes that way. I simply counted how many I needed. Okay, so there's limits you're going to hit. Compilers choose an arbitrary amount of work that they will allow in the constexpr context, and this is why complex processing like compression hits the limits, and I hit that quite early on. And so I had to make a more complex implementation that did the caching of the mapping between the character and the bits pattern for it, because previously walking the tree for every single character just was too much. It's still possible to hit the limits on large strings, but there is an override for your compiler. I'm going to move on quickly. There's a question about debugging. The most effective debugging I found was writing unit tests that run constexpr unit tests. And basically the compiler tells you what broke. And then you have to start dumping it. There's no real good support for stepping through it unless you can force the code to not be evaluated at compile time and try to run it locally. It's not easy. So USB configuration descriptions, I'll rush through this one so we get some time for questions if there are any, and if not, I'll be available after in GatherTown for a little while. This is, again, publicly available. I've only done USB configuration descriptions, though there's other types of descriptors that you would need for a full solution. And again, it's a very partial implementation of this, more to show the idea. Again, we'll just do it quickly. So this is a little bit more complex in terms of the types that we use, but it's probably not as complex in terms of the code. So configuration descriptor tells the host about the interfaces and endpoints. The interfaces are really functionality, like an audio stream or a keyboard, and endpoints are the data transfer addresses that are used in the USB protocol to send and receive information. We have a variable number of interfaces per configuration, and each interface has a variable number of endpoints. And so what we would like to do is use something that looks like this to build a descriptor. And in this case, I'm building a configuration object. The first sort of 4 parameters are fixed values. If you've played with USB before, you'll recognize those, but it's not really important what they are at the moment. And then I use a series of helper functions to generate specific interfaces. In this case, I've only really defined vendor-specific interfaces. The first one has 2 endpoints, one an in and one an out of different types, and the second interface has 4 different descriptors. And what we would like to see is all of that data gets calculated together. There's certain type information and size information that you need to have in the correct layout for the descriptor to be valid. So if we compile that and dump that section out, we get some data that looks like this, which, if you want to spend the time, you can go and check, looks like a real descriptor. So the way we do that is we use variadic templates. So the configuration, as you can see, is templated on a series of sizes, and that is applied to a variable list of interfaces coming into the configuration. Each interface then has a number of endpoints, and that's where that came in. And each endpoint is really just simple data. The helper functions essentially do the mapping from the list of endpoints that we provide as parameters into an array, and then return that type for the interface and similar for the endpoints. Rendering the descriptor is a little bit more tricky. Each class has a length method, so that would be the configuration has a length, and which uses the length in the interfaces, which uses the length in the endpoints. Each of them also has a render method that takes a span for the buffer that we're going to write into, and we then calculate the size of the buffer, call a render method to fill the array. Now the trick is we're going to use the tuple of those interfaces, so we can capture the set of different interface types, and we're going to use apply to call a templated lambda and then fold over the arguments in that lambda. So an example here, we have, again, we're using a concept, but it's not important. We take the configuration function, evaluate it, calculate the length, generate an array, and fill it. And it looks quite simple. So how would we calculate the length? We can see we have the tuples collecting all the interfaces together, and then we create the templated lambda, which we then apply all the interface types into, and we then fold over that calculating the length for each interface. And in a similar approach, we do the same for rendering, although we do need to track the location of the current position in the buffer. So we use a helper function for that, and we fold over that function. And again, we can deal with things like little endian writing and stuff like that as part of that. So I think that's pretty much all I need to cover, or I can cover. We're almost out of time, so questions are more than welcome. I'd like to say thank you for to the Hash Include C++ Discord for being a great community and so welcoming. And again, call out Jason for so much help and advice and encouragement to submit this talk. So any questions?